Okay, we just calculated the standard of error. Nope, we just calculated standard deviation, which is, again, how much your values are going to range from the average. Your sample values is like how spread the data is around the average. And now we're going to calculate even further the standard of error. The standard of error now isolates the average value itself. So standard deviation looked at how the values surrounding the average could vary. Now we're going to look at, well, how accurate is the average itself? So how accurate a calculated average population size is from the actual population size. Okay, and again, you don't have to memorize any formulas or any, what a different value or symbol means. You're just going to have to know maybe how to use it. So the standard error, we're going to take the standard deviation that we just calculated, and here they're using that lowercase sigma, the Greek letter sigma is the lowercase s, which is mighty convenient, of course, because when you actually had to calculate the standard deviation, they were using lowercase s in the English alphabet. But here we are. One way that I was thinking about, like right now, not to, because I will continually say standard deviation when I mean standard error. I'm trying to like mentally correct myself by just remembering like in the alphabet, letter D is going to come before the letter E. And you have to calculate the standard deviation first, like how much your values are deviating from the average before you can calculate your standard error. And again, the standard error is now looking not at values, but specifically the average itself. So you're going to take what you just calculated, the standard deviation, and divide it by the square root of n, where n is the number of samples that you took originally. When getting your values, a small standard error means that your calculated average population is actually pretty close and accurate to the actual population size. It's a good estimate. If you have a large standard of error, that means that there is a large fluctuation between what the actual average population size is and what you calculated. And so that would be indicative now that you would need to take more samples of your population, and that would just improve your accuracy overall. And if I don't know that I even made a note of this, but this is for population statistics. It's used heavily in ecology. So and also like in biological statistics, but it's used heavy in ecology. So anytime you're taking a population size. In AS level, you've learned the ways you could estimate a population would be by using like mark and recapture method, using a quadrat. Those are now we can estimate a population size by taking an average, but now we can look at that a little bit further. So again, standard deviation is looking at the values, all of your samples, like and how much they are on average, greater than or less than what the average is, your average population size. And then once we have that, we can look at the standard error and see how much your average itself, what you calculated, how much that value can actually deviate plus or minus the actual population size. We're going to use the same values again, the 27, 32, 29, 35, 25, 37, 21. And there is 7 of them. All right, now this part here, again, this is the standard deviation, how much your actual population size, like your sample counts, the 27, 32, 29, on average, how much those are fluctuating from the average that you calculated. And just to remind you, the average, we call that X with a hat, and that was 30.9. I'll just note that here so I don't. Okay. And yeah, we're gonna see now how much that average is accurate or how much it'll fluctuate. All right. So we know from the last example or the last practice we did, our standard deviation was 4.3. So again, that means that the 27, 32, 29, 35 on average fluctuated plus or minus 4.3 from this 30.9. And so I had that right here. So your average data range was from 26.6 to 35.2. Okay, so now to do the standard error, we are going to take fun sigma. This is also sigma, lowercase Greek letter s, or lowercase English letter s. We're going to take the sigma, which was 4.3, and we're going to divide it by the square root of the amount of population, or the amount of samples that you took. So you have to do the standard deviation before you can calculate the standard of error. And in the alphabet, D will come before the letter E. So in our numerator, you need to find the square root of n. N is your amount of data sets or your amount of samples, which is 7. When you do the square root of 7, and you should also do this with me, you'll get 2.67. Okay, and the third step now, you're going to divide the standard deviation, which is the sigma from the previous formula that we calculated right here. Okay, and we are going to divide that value by the square root of the amount of samples taken that you just did in number 2. And again, notice instead of calling it S, they are referring to it as a lowercase Greek letter s, sigma. Hooray. It's a sarcastic hooray. Okay, that sigma value, again, is this, the 4.3. And then we're going to divide it by the square root of our amount of samples that we took. All right, if you do 4.3 divided by 2.67, you will get 1.61. That is the standard error. So plus or minus 1.61 is an estimate regarding how much the average can be in an error. Where standard deviation, the first step that we did, is how much the sample values itself deviate outside of the average, plus or minus the average. And now we are just isolating, well, how accurate is our average then? Not just the sample sizes, but the average itself. And we're almost done. The most accurate way to use standard of error, and again, this is in biological statistics, regarding a sample size, is to use a confidence interval, and we're going to call that CI. And this is something too, I didn't want to mention a couple days ago because I didn't want it to be like, wait, what is she talking about? But in the experimental design and like the actual like setup questions, describe how you would set up an experiment to see the effective temperature on the amount of carbon dioxide production. This is also something you can add towards the end of that, whenever it's, you take your averages and then, you find the average, and then, you could say on that, to apply a standard error for the values with a 95% confidence interval. And I'll talk about the 95% right below here. And that will get you another mark. All right, so a confidence interval. Confidence is kind of like how certain you can be about how much your average could be different. So we understood our average from the beginning to be 30.9. And so the first thing we did was, okay, but how good are our values? Like how much are our values surrounding that average? And we said it was about 4.3 plus or minus, and that's pretty good. And if that value was really high and there was a lot of deviation from that, then maybe your method of sampling wasn't consistent, or maybe you went out at a different time of the day or a different type of tide, and that's causing a population to change a little bit. Maybe you had like different weather events happening. Oh, sorry, I'm gonna yawn. Okay. And now the standard error is like, cool, bet. How good is that 30.9 though? I'm sorry, yes, how good is that 30.9? So, we use confidence intervals to give an idea of how confident we are about a certain range of those averages, maybe how much they can be, how much the average could be higher than what it is, and what percent or how much of it could be lower than what it is. It's hard to talk about math without doing it first, but so the confidence interval. In biological sciences and biological statistics, it is standard to use a 95% confidence interval. And that's essentially saying that you are, after running the statistical test, you are confident that you can identify at least where 95% of the actual population, like the value of it, it's the actual population amount could be. So you have like a 95% certainty. Okay, and so the way we can calculate with further precision, this way we can say where 95% of the values can range around your average sample size. Again, the average sample size was X with a hat. Okay, and then we did calculate that average sample size in the first step of the standard deviation. It was 30.9. Yes, 30.9. All right, and this again is a test to assume or try and portray how accurate your population estimate is. Whatever the sample is. We do this in like social statistics too with humans, but definitely in like nature statistics, ecological statistics. All right, so to now assume a 95% confidence regarding the values that the average could actually be. So if it's not 30.9, we're going to run this last statistical test to see what they could be. So to calculate it, your confidence interval is 95%, and that is a standard. There are other confidence intervals you can use. I don't remember when you would use them. Like maybe you have to have a certain amount of a sample size, maybe like greater than 30 different samples where we only have 7 to run a different test. But 95%, even reflecting right now, that is what we used always in college as well. And that's all you will be possibly asked to know about. If you do take any biological sciences in college or go further in your bachelor degree in any biological sciences, you will also use 95% confidence interval. Okay. Again, you don't have to memorize the formulas. So you're going to do the average, all right, plus or minus your standard error. And you calculated the standard error up here. Okay, AKA take your average and then add and subtract 2 times the standard error. Okay, and this 2 times the standard error is exactly that is what you would do to get the 95% confidence interval. That is exactly what you do to get it. I believe a 99.7 confidence interval is just one standard error. You don't need to multiply it. But again, we don't need to regard ourselves with that. Like this is the gold standard is 2 times your standard error to get the 95% confidence interval, where you can say that like there 95% of what the average could be is going to be within this range. All right. So we're going to multiply the standard error by 2 to get the 95% confidence interval. Actually, that's fine. I just want it bigger. Okay, and our standard error, we calculated right here, and it was that 1.61. Point what? 2? 3.22? I don't trust myself. I'm tired. 2 times 1.61. Okay, 3.22. So this is the 95% confidence interval. This is it. And so now we have that. We're going to say, okay, what is the average then? Which was 30.9. That was the very first thing we calculated, and you've been taking averages of a population now since for a while, but since beginning of like AS level. Oh, I'm yawning again. Okay. So the next step and the final step in this analysis, add the answer from number 1, which is right here, to the mean value. And this is what you calculated all the way up here. 3.9 or 30.9. Adding the answer from number 1, which was your confidence interval, to your average population size that you calculated, that's going to give you the upper error limit. So this is the like here's the highest this value could be with 95% confidence. That's your X-hat. Plus 2 times the standard error. Again, standard of error was just calculated, the 1.61. When you multiply 2 by it, it's 3.22. And when you add those together, 34.12. So if we're saying we calculate the average to be 30.9, after all this now, we can say with 95% certainty, if it's going to be higher than this, if it's higher than that 30.9, wrong thing I highlighted. If it's higher than that 30.9, with 95% certainty, it's only going to be higher by a value of 3.22. So your high limit is going to be that 34.12 that we just calculated. That's the upper limit. The lower limit, again, we're going to take our average. And now this time we're going to subtract 2 times your standard error. And this is subtract the answer from number 1, which we got right here, that 3.22. from the mean value. And then this was the value we calculated in the very first step. And this is the lower limit of the, like, what the average could be. $27.68. There you go. Dun, dun, dun. Okay, so we can say with accuracy that 95% of the population, like the average size, but the population lies within the upper limit of 34.12 and the lower limit of 27.68. Those are pretty good, actually. Those are pretty good confidence intervals. And that's not a huge fluctuation either. And so essentially, if you graph this, it would look like the bell curve, where here's your average, the 30.9. And like here would be the 34.12. And this end, it's the 27.68. And you can round those as well. I didn't. So you have, again, 95% confidence, or confidence rather, that if this is going to deviate, if your actual population is deviating from that 30.9, the population average is going to deviate from 30.9, it is going to be somewhere within this 95% confidence interval. So it will lie within this range, and that's pretty good. So then you'll only have then what's remaining. If it's 95, then 5% left is remaining. So over here would be like, there's a 2.5% chance that the population is greater than 34.12. Over here, you're saying that there's, and that should actually be flat, but you're saying that there is a 2.5% chance that the population is less than the 27.68. Otherwise, you have 95% certainty, and that's great. If your confidence interval was pretty high, like higher than a 3.22, you would have like a much larger range of what your potential average population could be. So the last thing you can do is, once you have this, and it's possible they might give you a bar graph already made, or you have to do this yourself. Once you will graph your average. So I don't know this graph, I just looked for an example. Ha ha ha. All right, let's see this lady. What's that one looking like? I'll use this one. Isn't that amazing? It's amazing. Okay, so let's call this 350. And this graph again has nothing to do with the values we just did. But let's call that 350. And this error bar Looks like it's fluctuating plus or minus 50. It does. But what you're still going to do like normal, you will graph the average, which is what they did. So it looks like they graphed it up to the 350. Great. And then, because that's the average they calculated, I'm assuming, pretty close to it. And then once they ran their statistical test, they did the standard ABCD. Okay, standard deviation, and then found the standard error, so how much the average could deviate, and then multiplied the standard error by 2 to get your 95% confidence interval. You're always multiplying by 2, always by 2, always by 2, always by 2, always by 2 for the 95%. It's always by 2. Double it. And then they took the confidence interval and added it to the average. And again, this average looks like it's 350. And so I imagine they said, okay, it could be 400. So then they took their data there and they put, this is 400, right? They did an error bar right here. And they said, yeah, but then if I also look at the lower range, and again, I'm assuming just from eyeballing it, they're saying their average is 350, but it could deviate plus or minus 50, it looks like. If this is here's 300. Okay, this was their lower limit. It could be right here. And you're also going to use a ruler for these, and then you will connect them with a ruler. And that's how you can plot an error bar on a graph. So you'll always do the average, like you always have. Average, 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 average. And then you're going to take your average and you're going to go plus and minus your confidence interval at 95%. And then to get, again, the confidence interval at 95%, you're going to go 2 times the standard error. Standard error is the standard deviation divided by the square root of your sample size. Ooh, it's 1 a.m. and I remember that, and hats off to me. Okay. Lovely, lovely, lovely. The only thing, and I keep saying you don't have to memorize these, but the only thing you will have to know, if they give you a confidence interval and they want you to calculate it at 95%, you need to multiply by 2. And I'll remind you that so many times until Monday. 95% confidence interval so that you can be certain about where 95% of the potential averages would lie. 2 times your standard error. They'll give you standard error, I imagine, as well. Okay. All right, cool.